Okay, time to start. So today we are going to, hello. Woo. So today we are going to talk about synchronous reactive models. Now, synchronous reactive models, a little history. So they are coming from the French community of synchronous reactive languages. So there are a family of languages that have been developed in France. Some of them are called Esterel, Signal, Lustre, that are all related to this model of computation. And the idea was to make computer languages deterministic so that you know what they do, right? So we know that the basic problem of computer science is the fact that the Turing machine itself, the halting problem of the Turing machine, is undecidable. So this is the root of all possible evil, right? Because we don't know what the computer program does, essentially. We can't even say if it terminates or not. We have no proof, right? So the only way is just to run it and see if it goes, right? So not a good situation. So if you look at circuit design, and this approach by the French community come from the hardware design side. So in circuit design in the 70s, everybody was designing asynchronous circuit, right? And so the problems were about the fact that you had race conditions, so the actual results, the output of what you design depends on the data. So you cannot say that immaterial what the data is, the function of this hardware computes is always the same. It's not the case, because according to the race conditions, so on and so forth, you may have different results. So, and this was creating, of course, all kind of nightmares. So what people resorted to is they tried all possible inputs, and off you go. Remember that in the 70s, the largest circuit that people could realize were about 16 transistors, so big deal. You know, I can do it in my sleep. Blah, 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 blah. Yeah, it works, hallelujah. Right. Now, when you start increasing the complexity of a circuit, this kind of analysis ain't going to work. So you have two options, right? One option is analyze to death, so simulation, 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 simulation. But again, the confidence of the result depends on how many simulation vectors you tried. And so how well you visited the input space. And so there is no guarantee that if the simulation result tells you that the circuit is okay, it is really okay. If it says it's broken, it is broken, no problem. But if it says okay, it's okay as long as I look at my inputs. That's one. Or you derive some formal techniques, whatever, proof, proof theorem, and all that kind of stuff, which is not exactly scalable. So then, the alternative is that not to have the problem. So you eliminate the problem by construction. And so the circuit guys say, how do we eliminate the problem of race conditions? And the idea came by saying, okay, we put boundaries to the computation by inserting latches in the circuit and inserting a clock signal that makes me read what is in the latch at the time that I decide to be. And that's a clock cycle, right, what we always say. So computers, for example, when they say is 1 gigahertz computer, it means that the clock cycle is 1 gigahertz, right, is what determines the reading of the computation. Now, again, and if you look at the computation by putting these latches, what happens is that in between clock ticks, you don't care what is going on. The only thing you care is when the clock tick comes, right? And so if you let enough time in the clock period for a circuit to settle, then the computation is unique. So you have a deterministic output. So you always know that what you compute does not depend on the data. Okay, so it's a generic result. So of course the value depends on the data, but the fact that if your circuit is correct or not does not depend on the data. Great. So that was the beginning of a beautiful friendship. So we got lots of results, Intel went on and designed a huge microprocessor and all that based on this principle. Now, then the French people said, wait a minute, why all these guys cannot write a damn program that works? Say, why can't we use the same reasoning? So if indeed the asynchronicity of implicit in the Turing model is what causes all the angst about writing correct programs, well, we use the concept, a similar concept as what we use for the hardware, in the sense that we are going to assume that all the components of the software program work in lockstep. Right? So they go together, which means that at some point, that's the reason why they're called reactive. Okay? Synchronous, we just said, but reactive means when an input comes, then you look at all variables in the computer program when that input comes, and then you decide what to do. So it's like you take a snapshot of the entire system, and you decide on that snapshot what to do next. Okay? That is the synchronicity. Reactivity comes, something happens, and you take an action. And that action, though, is to look at the entire space of all the variables of the system. And based on this value, you decide where you're going to go. So you do computation, right? And then you settle, and then you wait for another input to come in, and off you go. So that is the principle of synchronous reactive models. Now, when I said everything settles, now the point is that in circuit you can say that because there are physical systems. But in abstraction, in computer languages, we know the time is not there, right? So what does it mean when all settles? It means nothing. Essentially, everything happens immediately, right? So there is no time, right? So instead of saying immediately, you say time is not there. So whatever you compute is what it is, right? So you don't need to wait until it settles. It's a concept that doesn't exist. You compute immediately, right? And then you wait for the next input to come. Now, these friends of mine, so we wrote several papers together with this community of French guys. I almost wanted to kill them because they did something very bad. In what sense? Because they said that in this model of computation takes 0 time and communication takes 0 time. What is wrong with it? Anyone volunteers? And why it was so upsetting, at least me. I don't know how many other people. Yes? Unrealistic, always is unrealistic. I mean, when we work in the abstraction, also computer languages are unrealistic. There's no time, right? So, any other person wants to volunteer? When they say it's 0 time. It implies that there is time, but we just say the time is not part of a model. So they shouldn't say 0 time. They should never say that because you mess up things. And you come up with the right observation. Yes, I say, what the heck, 0 time? It is impossible, right? The point is that time is orthogonal to the model. No time. So they say computation occurs in a separate cycle than communication. That's all there is. So time does not matter. There is no time in the model. So if they tell me 0 time, I'm going to kill them. So I kill them. Okay, so no, I mean, figuratively speaking. So we had all kind of nice. So we came up with the idea, logical time. Also, this one is kind of upsetting me. But logical time, okay, I can get that going, right? So at some point on, the Turkey-French people say logical time. Okay, we can discuss it because it's not real time. So it's no notion of time, and that's fine. So then everything occurs in logical time, which means logical time is only ticks, right? It's only discrete jumps that we like, at least I like, to call reaction index, not time. Reaction index is an index, right? Because it's a sequence of such computation. So it's an index in the sequence. Okay. Now, this is what synchronous reactive models are. Now, this presentation here, since there are a few tricky points that you have to keep in mind, is very much based, I mean, this the lecture last year was given by Stavros Tripakis, who is an associate of the department. he decided to do the analysis using circuits, right, and the logic circuits. So we will use that because, again, logic circuits relate very much to the way in which the French people came about. Okay, so we said already, composing discrete system, there are two major paradigms, synchronous, asynchronous. Synchronous means that everything occurs in lockstep, and asynchronous, everybody's free to do whatever, right? So whenever something becomes available, you compute on it. Okay, so the fundamental characteristic of synchronous systems is this idea of a synchronous round, which is a synchronous round is between one reaction index and the next, is a round of computation, right? So the rounds are, for example, you start the round, you have inputs, outputs produced, and then you start the next round, inputs, outputs are produced, next round, inputs, outputs, and so on. Oops, too much. Okay. Now, the point that I don't like about this figure is because you have the inputs and outputs in between. That's not exactly right? Because there shouldn't be an in-between. But, you've got to have a picture, right? But remember that every time there is a reaction index, input and output occur at that reaction index. Not in between, at that reaction index, okay? So, anyway, this is a picture just to show that in the round something happens. But the important point is that we read the inputs, we give the inputs, and we read the outputs at the reaction index instantaneously. Same reaction index, okay? So everything happens all together. So let's take this synchronous block diagram. You have A, B, C. Now, I want you to think about, so suppose that and a round is when you compute all the blocks, right? Because remember what I said. When we have a reaction index, everything has to compute, right? Everything happens. Now, assume that we are in an asynchronous model, right? So is this diagram always giving you the same answer or not? Or potentially you may have something different. Now, if it is an asynchronous thing, then A may have delays inside, right, asynchronous. So the output, which is the input to B, may occur before the output that feeds C. So you will see a particular computation that gives me the output of B first and the output of C later, right? Assume that the input is such that the delays are reverted. Now, in that particular case, you see C first and then B. It's a different computation, right? And so this is data dependent. It depends on the input, which circuitry is exercising inside the block. Okay? Now, assume that we are in this wonderful synchronous world, right? So the only thing we do is that A produces an output which doesn't have time. Instantaneously, B and C compute their output. Okay? So there is no ambiguity. Given an input, that's what you read. The output of B and C. End of story. Okay? So you see that by using this, synchronous model, this particular diagram has no ambiguity whatsoever. So it's deterministic. It's fully deterministic. And in fact, you can compute. When you implement the circuit with the synchronous assumption, you can do B and C in parallel. You can do B before C. You can do C before B. Nothing changes because you read after this is done. Okay? In the implementation. Now, when we're talking about the model, there is no notion of time, so it doesn't matter. B, C, parallel. It doesn't have any sense, right? It doesn't make sense how you do it, right? Because it is a logical specification of what the system does. Okay, so this is called deterministic concurrency. Now, the thread model that you have seen before, which is what, for example, computers use to speed up computation, is that they pick up fragments of the code that can run in parallel, quote unquote, and then they interleave, right? So it is an asynchronous model. And so that is the reason why threads are bad. Right? It's very good because speed up the computation, but are bad in the sense that complicate the analysis. Okay? So not so very good. So it's much better to use a model computation that gives you the exact meaning of a computation itself. So we said before, threads yield incomprehensible behavior. So now we want to exploit this model computation, synchronous reactive, and it is a computer program, by the way. So they have constructs, they have all kinds of stuff, STRL and Lustre and Signal. And, for example, STRL is very much used in designing trains. And the train, synchronization, right? When the bar come and the rail switches and all that kind of stuff. You don't want to mess that up because of a race condition, right? So, boom. It can still happen, but because something breaks, but not because of a model of computation. So, STRL is very much used in that domain. Lustre and Signal are very much used in airplane, avionics. And so much so because the Lustre compiler can be proven correct. So it's correct by construction. So, of course, you can always mess up the algorithm, right? There's nothing. But the implementation of the algorithm in that language is always correct. Hallelujah. That's very good. Now, where can you get into trouble is in performance. And performance on one side is the speed, because you have to, quote unquote, when you implement, you have to wait for the tick, right? When you implement. Or because, remember that at every reaction index, I have to look at all the outputs of all the blocks. And so some of these, there is no need to look at them because they don't do anything. But I don't know, and so I have to look at all of them. Because the model computation say you have to look at all of them. So you get the advantage of being correct, quote unquote, by construction. You may be hit on the performance side. That is the reason why people still use C, C++, and all that kind of crap, right? Seriously speaking. Instead of using these wonderful languages, because you may have an impact on performance. So then, hallelujah, so we're still working, trying to figure out how to combine the performance of one model with the beauty of the other model. And there are all kinds of things that one can try. Anyway, so now, since we're talking about synchronous systems, then it's natural to investigate this model computation using finite state machines, because finite state machines in per se are going according to reaction index, if they are alone. Now, we are talking here about concurrent systems, which means that my system is a bunch of finite state machines, okay? Not just single one. And we have to see how we are going to combine them, okay? So when you combine parts, there are two or three things that you need to say. One is the behavior of the part. Two is the communication pattern. So, for example, the output of his output goes into him, and his output goes into me, and my input goes into him. That's a communication pattern. It's how the input and output variables are set. And so that's when you write a diagram with things and arrows, that's what it means as a communication pattern. And the last thing is that what communication means, right? Because the fact that I put an arrow between me and him, what does it mean? So these are the different things that you have to say when you study concurrent models. Now, again, because your book is based on the notion of actors, we will use the actor model of finite state machine. Here is kind of tricky, because we will see that in certain way of connecting subsystems, we really cannot reason on the entire signal. You have to go step by step. Remember that the actor model has inputs which are waveforms, right? Waveforms meaning sequences of values, and the output is all sequences of values as well, okay? So it's not point by point, right? It's the entire boom, right? The entire shebang. And so that's the actor model. So an input is a waveform, and the output is a waveform. Okay. So, in fact, the system then is a function that accepts input signal and yields an output signal, which implies that the S goes from capital X to capital Y. Well, capital X is the space of function over the reals. Okay? So remember, it's like I inject the entire waveform. I want to see what is the output wave. All right? Okay. Now, there are different ways in which you compose a finite state machine. Since everything happens in lockstep in the synchronous reactive model, the most used way of combining things is called the synchronous parallel composition. So parallel composition. Now, in your book, it says side-by-side composition, right? And why do we say side-by-side composition in the book? Because parallel, you always think about, like in circuit, right? When you have a resistor or capacitor in parallel. That's not the case. Here in parallel means that is the combined behavior is the product of the two behaviors. So it's nothing to do with the fact that the input and output connect in any particular way. It's the way in which we build the overall model of a system that is called parallel composition. So parallel has nothing to do with the connection. It's just the mechanism according to which we combine two finite state machines. And so what is it? How do we combine the model in a parallel composition? So assume that I am a finite state machine, and here to the right is another finite state machine. Okay? Now the parallel composition, remember everything happens in lockstep, says input come in, I take a step, my friend here takes a step. So the system goes from the pair of initial conditions for me and my friend to a pair of states that is my next state and my friend next state. So given a particular set of inputs that go to the two machines, you go to a state in machine 1 and a state in machine 2. So it's as if you had a single finite state machine where the states are given by all the pairs of states. And the transition in the composed machine exists if the corresponding transition in the two machines occur. Okay, that's called parallel composition. Okay, that's what it is. So you go together. It's like side by side. It's like you grab your friend and you move in lockstep, right? Synchronous reactive model. Okay. Now, this is independent of the fact that my output can combine with this input. Remember that in the model of computation, I take a step, he takes a step. The fact that my output are his inputs forces him to take a particular path in his trajectory, but the composition is the same. So we are going to, when something occurs, everything computes, boom. And then he takes his next step, I take my next step, we combine, and that transition belongs to the transition of a combined system. So that's the way you should think about it. So reactions are simultaneous and instantaneous, meaning no time, okay? So they happen together, right? That's what it means, right? Together, where togetherness means you don't wait to do the computation, because you could wait to do the computation, right? So if I have a causality relationship impressed by the arc, then I should wait. But since we are moving in lockstep, everything happens all together. So, okay, so consider a cascade composition like this, right? So you have a finite state machine to the left and the finite state machine to the right. So an input comes in, which is A, right? What will be the composed model of this machine? So how many states are you going to get? Right. 4 is a product, because I have to look at all the possible composition of different states in the different two machines. So it's the product of the two machines. Okay, so it's going to be S1, S3, S1, S4, S2, S3, and S2, S4. So these are the 4 states of the composition. Now, then I want to see when I should take an arc between these composed states, right? and what the input and output should be corresponding to that movement. Now, this is you see S1, S3, S1, S4, S2, S4, S2, S3. So this is the composition. Now, I come in with A. Now, if A is present, then I output B, and I stay in S1. Okay? Now, if A is not present, I go to S2, and then I come back to S1, putting out nothing. Okay, now, what does this say? It says that if B is present, then I'm outputting C, and I stay there. If I have no input, no presence of B, then I go to S4, and then I come back, always come back, outputting nothing. Now, the composition as primary input A, we call them primary inputs. So they're the inputs to the combination of the system, and as primary output C. And B is an internal variable. So then, if A is present, I stay here, but A outputs B, so B is present, so it outputs C. So machine 1 is an S1, and machine 2 is an S3. So S1, S3, if A is present, always outputs C and stays there. Okay? Now, if A is not there, is not present, right, what do? I go to S2. But if A is not present, it outputs nothing, right? So B is not there, so B takes a transition and goes in S4, right? Okay, so I have to go to S2, S4. Bingo, right? Under the condition not A, right? Because not B is the same, right? Not A. And then I always come back. So I come back to S1, S3 on true. So since we exhausted all the possible combination of input, right? So we said, okay, so this is a finite state machine. Yes and no, because we have these other states that we have to take care of. Now, because we have walked through the machine, it's obvious that what we will come out for the other states is going to be a set of unreachable states, because otherwise we would have seen it. And we have taken all possible combination of inputs, right? Present, absent. So in fact, if you want to do, say, S1, S4, so you have to assume that you are in this composition, S1 and S4. And so S1 and S4 here in this composition, if you assume that A is present, then it goes to S1 and S3, takes this, and it doesn't output anything. If A is not present in S1 and S4, then it outputs nothing, goes to S2 and S3, but S2, S3 have a transition that is always taken, but spits out nothing. So which means that you cannot go from S1, S3, S2, S4 to S1, S4, S2, S3. Which then means that these states on the bottom can be thrown out. They are unreachable states, so you can throw them out. So in fact, in the compositional machine, it's true that in the worst case, the number of states is the product of the two states, right? And if you have three machines to compose, it's the product of N1 cross N2 cross N3. So it's an exponential growing number of states. The good thing is that often the actual finite state machine is full of states that are not reachable, so that the complexity is less than that. But you have still to look at all the combinations and determine if the states are relevant or non-relevant. There are plenty of literature that goes around and says how you should form the composition machine quickly, right? You can compose implicitly. There are all kinds of very nice algorithms, because this is a basis. When you look at, you analyze a large system, the basis is to combine the components. And so you want to do that efficiently. Okay. So these are unreachable, throw them away. Keep on going. Ha-ha! Now this one is a pest of a pest of a pest. Right? Now remember that feedback is a very good thing, because with feedback we can fix things, right? Control theory is all based on the feedback, right? On the fact that output feeds back in the input, and then you have a reference signal, and then you look at the difference between the reference signal and what comes out, and you take action to make what you want. This difference is an important information. Now, on the other hand, we also know that feedback can be tricky. Why? Because the communication is between a machine and itself. And what that signal that goes like this says is that in every reaction, I have to have that the output A2 has to be equal to the input A2. Okay? Now, who tells me that that should be the case? Right? So this is the tricky part. There are ways in which if you assume certain things on the system, then this is always well-defined. But there are many compositions which this is not well-defined, meaning that you can never find a way of operating of a system which the output is equal to the input. Okay? All right. So, interestingly enough, if the block that is fed back like this is a physical system and has ordinary differential equation written in the form x dot equal to f of x, that thing makes sense, it always exists, and you can construct the feedback signal always. Okay? So, hallelujah. But you have to have the equations of the block written as x dot equal to f of x. If you had f of x dot x and u, you are not sure. It has to be written exactly like what I say. X dot equal to f of x and u. Otherwise, you can claim a priori that the things work. By the same token, if indeed the block in there is a finite state machine of type Moore, this always works. If it is a machine that is type Mealy, not necessarily. You may or may not have a well-defined composition. Now, I know that you already seen, yes? No, because we are talking in the domain of finite state machines. So a finite state machine intrinsically is never time triggered. And then it's a single system, right? So it doesn't make much sense to be time trigger. It's the same thing, right? When you have two things, then you can say time trigger or event driven. But if you have a single thing, it's the same thing, time trigger or event driven, right? Because it's a reactive model. Okay, so I put an input, something happens, and then, okay. Now, who knows why, or at least as an idea, why if the finite state machine is a Moore machine, it works, and why if you have a Mealy machine, it may not work? Any wild idea? What is the difference between a Moore machine and a Mealy machine, first of all? Okay. Not quite. Yes. Bravo. Yeah. Only of a state. Okay? So that is the key difference, right? So now, if the output is a function of a state, right? But what function? In which state? You are talking about the state, previous state, right? Because we are talking, it's not after the transition, it's at the transition. So, which is something that is well known. It doesn't change. So the output is well defined. Okay? Should be. Now, the problem with the Mealy machine is that the relationship between the output and the input is instantaneous. So there is no delay. And so anything in a feedback loop where there is no delay, you may or may not have a solution. And if you have a solution, you may have more than one. Shocks. Right? That's bad news. Okay, so let's analyze this. Oops, did too much. So, okay. Now, interesting point is that no matter how complicated your stuff is, you can always aggregate things in such a way that is a function f together with a feedback loop. Yes? Same thing.
What's the dot?
Derivatives, dx dt. It introduces delays. Remember that, for example, in physics. Yes. Of course, in continuous time, yes, right? dx dt. No, but we have a reaction index. And what it says is that the reaction index here depends on the state of the previous reaction index. No. When I talk about x dot equal to f of x, I'm talking about continuous system. So there is no finite state machine, no nothing, right? It's a dynamical system. And so in dynamical system, I hope that you have done some control class. And then the whole point is to have the controller, right, which takes the output and fits that back into the input. And then the equation here is x dot equal to f of x is the basic thing. And then you have y equal to u to introduce the thing. Now, if you have x dot equal to f of x, what happens is that the way in which x changes, the derivative is continuous, right? If f is Lipschitz continuous, which means that I cannot make jumps, which means that my x of t is delayed, which means that the output is delayed with respect to the input. That is enough to guarantee me that I don't get into trouble. Okay. So in fact, it's funny because the Theano-Picard-Lindelof theorem of the existence and uniqueness of the solution of a differential equation is based only on the assumption that f of x is continuous. Now, and that continuity means that the derivative of the trajectory of the solution is continuous, which means that no jumps. No jumps, everything is fine. Okay. Now, in the discrete domain, this translates into what is the delay then. And there is no time in the discrete. So I use the Moore model to introduce the notion previously, right? Previous reaction index. So that's what the translation is. So Moore machine is the same as x dot equal to f of x. That's essential with respect to feedback. Okay, so anyway, no matter how complicated your system is, you can always reduce it but via a series of parallel composition to be a system with a feedback on top of it. Now, if you don't have feedback, hallelujah, but 99 out of 100 a system of interest do have the feedback. So you got to deal with this stuff, right? Okay. So given the fact that I can always combine my system in many different ways until I get to that thing, I have to say, what does it mean to have a system with that feedback, right? What does it mean? How do I compute that signal S that is the results of the feedback, right? So you must have already seen where we are going to go. Is that, okay, this is a continuous system, the x dot, that I was talking about before. And so in this particular domain, you see that theta dot y of t is equal to theta dot y at time 0 plus 1 over I y integral from 0 to t of the input, which is ty tau in d tau. That is where the delay comes in, right? It's the integral operation that smooths out things, right? So this one is equivalent to this. Now, tau y is equal to psi of t, which is the primary input, minus the feedback signal that comes in, which is the input E of the controller K. And so when I look at theta dot y here, and I look at theta dot y here. So there is a variable that occurs on the right and on the left, which then means that in order to find the value of that variable, I have to solve that equation. Now, again, remember what I said before. If you assume that this function the derivative function is continuous, because of the integral, this is always a solution. Okay? So, hallelujah. So this feedback is well defined in this particular case. Not always, but in this particular case it is. But this is what the meaning of a feedback is, that simply you feedback the output signal with respect to the reference signal, and you drive the system. Okay. Now, again, we said that easy when state machine is type Moore is complicated because it's Mealy for the same reason. So the derivative is equivalent to taking one step delay, call it. Okay. So Moore versus Mealy machine. So Moore machines are such that the output depends only on the state. And so the representation of a Moore machine, it doesn't have to have a transition labeled by the output. you can label the states with the output because the output depends only on the state. Okay, so and this also tells you that when you land in the state, then the output is computed. Okay, so which means that when you compute the transition, you have to take previous reaction index, which makes life easy. Okay, so that's the thing. So Moore machine circuit view means that you are pulling out the output function out of the state, and the state is sitting in the latch, and so you read the state out of that, and you compute with the resistive circuit the output of it. Okay, and so which means again that you are taking the results of a previous reaction index. Okay. So how to define feedback? Separating output from state update function is necessary to define feedback easily. So I take yn, I put it back into xn. The fact that there is an output that reads out of a latch is essential in this situation. Okay, Mealy machines, well, we have to label the transition with the output because now the output depends on the transition, does not depend on the state. So in fact, you can see that in S0, if you take one transition, the output, let's see, which one? S2, is always 0. So this one is ill-defined thing because it's as equivalent of the Moore machine. So even though the idea was to give it as Mealy, this one is a Moore machine. So, okay, forget it. But the idea, which one? S1? Because I have, yes, correct. Because I have, yes, I have 0 or 1. Yes, according to the transition, right? If I had 1, 0 and 0, 0, then it would be a Moore machine, okay? So I look at all the transitions except that. Thank you for pointing it out. So this one is a Mealy machine because the output is not only function of the state, it's also function, instantaneous function of the input. Mealy machine, the view is this one. You see that the input feeds directly the output. Okay, so it's a zero delay, quote unquote, zero transition impact on the output from the input. So feedback from the Mealy machine, again, you take yn and you feed back into xn, and all of a sudden you got something that is instantaneous. So there is instantaneous logic dependency. So now, we said before, what is the meaning of this writing? So this one is a symbolic writing, right? It's a box with an arc around. So the meaning of that is the same thing as we've seen in the continuous system, in which we had one variable which appears on the left and appears on the right. So why? Because you say S, suppose the signal S comes here. This output is F of S. And now, to impose the feedback, you have to say that S is equal to F of S. Okay? So if that equation has a solution, then this is well defined. If you have no solution, it's inconsistent. If you have multiple solutions, it's not deterministic. Right? Because you may have different behaviors given the same situation, the same. Okay? So the meaning is S equal to F of S. Now, have you seen this before in any of your classes? X equal to F of X. What is it called? Come on, guys. No. No. It's the fixed point equation. X equal to F of X, right? Now, how did they... Well, boy, God, you've not seen this. Ouch. Now, is that for whoever now remembers this beautiful equation, X equal to F of X, what is the simplest way of computing the solution of X equal to F of X? Yeah. So what you do is that you start from X0, then you put into the F, right, and you grind it, and it comes out F of X0. Now you feed it back and say, oops, it's not equal to X0. Now, what do? Then I take F of X0 and I put into the machine, right? and it comes out f of x0, right? And when I say, is f of x0 equal to x0? No. So I keep on going, right? I keep on going. Now, what do you think will happen? Grinding. Do I get to some place or not? Sometimes. Very good. Sometimes. Does anyone remember what is the condition on f to make sure that the thing is a sufficient condition? It's not necessary. And now, mind you, there are tons of results in mathematics about this damn equation, x equal to f of x. You say, well, gee, what is so? You have topology that is saying, well, under what condition x equal to f of x has at least a solution. And that's called the Brewer fixed point. So if it is a mapping of the unit ball into itself, it always has a fixed point. I'm not asking that. It's too complicated, topology. Forget it. Something more simpler, right? Simpler than this. Yes? Ni. It has to be monotonic in a certain sense, because you can have monotonic increasing, not so very good, right? Because what happens is that x0, put in f of x0 bigger than x0, then you put back in f of x0 is big, so never converge. So, not enough. Yeah, it is enough for a Brewer theorem, but in general, for the iteration to converge, is f must be a contraction mapping, which means you put in something small and it comes something and it comes back smaller. Then at some point, smaller, at certain point converges, right? Because you keep on cutting down, at some point you get there, right? So x equal to f of x has a solution. Everything is a contraction, right? Thank God, in the case of these systems here, we can do, instead of looking at condition under which the map is a contraction, we can have a constructive similar to x, to what we were saying, to the grinding machine, right? You put in x0, you see what happens when you put down f of x0, call it x1, grind again, and we do exactly the same thing. So we are going to operate in the same manner to figure out what is going on in this thing. So reorganize abstract actor, abstract signal, there you go. So we seek any S belonging to Sn such that f of s is equal to S. Such S is called a fixed point. Okay, and it is the behavior of the system. So it's what the system does, right? Okay. Now, data types. Now, first thing that you want to know is that, well, if I'm feeding back y into the system, of course y has to be in the space of the input. Because if the input is apples and you put in oranges, then the f, it says, I don't know what to do. I only know how to do apples. Don't feed me oranges. So that is inconsistency in the data type. Right? So data types, think always of data types, oranges, apples. That's what it is. Nothing more, nothing less. So apples to apples, oranges to oranges. Okay. So that's what this thing means. Okay. So there is also the concept of the firing function, and the firing function is when you take a step into the iteration, right? Okay, so we are going to use a sequence of firing function to see if this thing does something or not. Okay. Well-formed feedback. A well-formed feedback is when it converges to one thing, right? So x equal to y. So at some point, this I can find the solution. That's well-formed. Is ill-formed if I can't find a single solution. I can find multiple or no solution. Okay? So this the notion of well-formed or ill-formed. Okay. Now, how to determine whether a system is well-formed? Now, cyclic circuit, as I said before, this one is a cyclic combination. You see that the output is fed back into input in this particular case. Now, anyone says that this has a fixed point or not? Any wild idea? So try x equal to 0. So what happens? X equal to 0, you have an end. So no matter what the other input is, it's always 0. So bingo. Now, okay, for x equal to 0, everything is fine. Now put in x equal to 1. Okay? So now 1 and, so it's equivalent to the input which is fed back. Now, but x is equal to 1, this is an OR. So what is the output? 1. So feedback there, okay, bingo, right? Found. So this is a well-formed circuit, because no matter if x is equal to 0 to 1, we know what happens. Okay? Hallelujah. Even though this is bad stuff, because there is no latch, no nothing, right? So this is a fixed point with direct influence of the output on the input at the same reaction index, because it's not a finite state machine. Okay. Now this one is a cyclic combinational circuit. This is a select operator. It says if C, then you take f of g of x, else you take g of f of x. Now, is this well formed or not? It is. But it is, in fact, it's a selector. It's a standard circuit that you use. So not always, if you have a feedback, is bad news. You can define some interesting compact circuit to do what you want. Is there an equivalent cyclic circuit? This is a standard question, and the answer is yes, but it's much bigger. Okay, so sometimes people use these circuits with feedback, instantaneous feedback, to cut down on the size of a circuit. But you potentially run into problems. So the trade-off is there. And I don't know anyone who is able to do, except for simple circuit, to exploit instantaneous feedback to make the circuit smaller. Okay. All right. So now on the right is a classical example in circuit that people say, "Ooh, bad." Right? Why is that? Because the input is 0, the output is 1, and 1 is different from 0. So that circuit, bad, no solution, is ill-formed, right? Bad. Now, but it has a use. What is that? I mean, did any one of you design, logic design, circuit design? Do you know what that is? Oscillator. But oscillator what? It oscillates only if you put a delay. So in physical circuit, there is always a delay. And so that thing kind of boom, 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 and that is an oscillator. That's the way in which you indicate an oscillator in your circuit. But remember, it has to be a delay, and it is a physical implementation of that diagram. Because that diagram, from a logic point of view, doesn't make any sense. Okay? Now, go to the right. Then this one is okay, right? You can find a fixed point. But unfortunately, you can find 2 fixed points. It can be 0 or 1. Right? Both of them are okay. So it's non-deterministic. So you don't know what this thing does unless you introduce delay, and then it oscillates. Hallelujah. Okay. What about this one? Any wild idea? So now, what is the difference with respect to before? Because this one is a NOR gate, and the input to the AND gate is negated. So this is bad news, right? It doesn't work. Okay. Why? Because you have a possible oscillation in Y. So if the variable that goes around may oscillate. It doesn't have a... So the overall circuit doesn't make sense. But if you look at it from the input and output point of view, you always can find a solution, right? But inside, there is something that goes on that is not nice. Reason being is that variable inside is non-observable. So, in fact, that's the reason why sometimes people say that you should have observability in your systems, because this may cause instability and the circuit to burn up. So the circuit computes what it's supposed to, but inside there is an oscillation, and so you have power consumption, all kind of bad stuff. Okay. So now, constructive circuits are things that are guaranteed not to oscillate. Constructive means that you can compute the fixed point using the grinding machine. That's all there is. And there's my friend, again, one of these guys of the French community, Gérard Berry, that used this to establish a symmetry between the hardware and the software implementation. Because in software, you can write something like this as well. Okay. So, although the cycle does not affect the output Z, this circuit may be problematic for what we said. It can be unstable and all kind of stuff. So a constructive circuit is always well-formed because we have a machinery that gives us the fixed point. So it's well-formed. Right? It's like F is a contraction mapping. We know the fixed point exists. But we may have a fixed point even though F is not a contraction. Same thing here. We may have a circuit that is non-constructive, and yet it may have a single solution. So now, what is the grinding machine? The grinding machine is the following. You start with all the value of your circuit to unknown. So I don't know if it is a 0 or 1, okay? Except the input that I know, right? And then I start propagating the signal around and see what happens of the unknown. Now, if I have unknown or 1, we know that is 1. The output is 1. If I have unknown and 0, we know that the output is 0, no matter what the unknown is. So doing this simplification, either we converge, so all the unknown go away, or they don't. If all the things go away, we say that we reach the fixed point, and this circuit is constructive. Why is constructive? Because it builds the solution by this iteration process, right? Okay. So analyzing circuits. So using the constructive fixed point. So take this. 0 and something, the output is always 0, right? Then 0 and 0 is 0, so this is okay, right? My constructive approach will tell me that the fixed point exists. Bingo. Fixed point reached. Okay. Now, this one, 1 and something. Is that a constructive circuit or not? No. Very good. Because the feedback is always unknown. I don't know what it is, because 1 is killing everything. Okay. Now, second one. No. Right. You are on the ball today. Last one. Yes. Good. Okay. Excellent. Okay. Now, more example. So we initialize with input values and unknown on other nodes, and then we keep on going. And so we will see that in this particular case, I eliminate all the unknown. In this particular case, the unknown in there is not eliminated, which implies I don't know what is going on, and so it may be bad. I don't like it, right? So, but it has a fixed point. It does have a fixed point. But it's not constructive, right? And in fact, there is a part of the circuit is bad, 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 okay? Okay, evaluate the lower gates, that is trivial, right? So 1, 1, 1, everything works, and you are happy. Now, in the particular case where you have on that side the negation, then you get that, but the feedback variable is always unknown, okay? And so that's the reason why it's bad, okay? So unknown nodes remain. Constructive semantics rejects this circuit, say, go away. And you say, well, I have a fixed point, but the constructive semantics say, yeah, but you have other problems that you don't see. Okay. Now, again, the equation f of s equal to s can be also interpreted in classic logic. So only 0, 1, true, false, and no unknown value. And so there are bad circuits with unique fixed point in classic logic. So if you go through the analysis of this thing, you say logically the output of the AND gate is always 0. But if x is equal to 0 and the inverters have delay, then this circuit will oscillate. Okay. Now, let's apply this principle to state machines. So this is my finite state machine that you see there. And then I'm putting B equal to A. Now, the question is, what does that finite state machine do? Okay. All right. So in state S1, no matter what, we have a S of n, which is the output, if you like, of the system, which is always absent, right? Because I am in S1, A is the A present gives me no presence in the output. B present doesn't do anything because the output is not defined as yet. So in S1, there is no B to be talked about. So we get unique S1 equal absent. In state S2, then we always get Sn present. Why? Because the input is not A, I get B. And if the input is A, I get B again. Yes? Say it again. Not necessarily. Yeah, well, you can assume also that it can stutter, right? There's no issue there. So anyway, hence S alternates between absent and present. So B, the output, is absent, then it becomes present, then it becomes absent, then it becomes present. And if the fixed point is a waveform with done absent, present, absent, present, absent, present. And it's consistent, right? Because it's not oscillating at the same reaction index. Remember, now we have a finite state machine. And so there is reaction indices that take place. It's not static like the circuit that we have seen before. So this one is a well-defined machine. It actually is equivalent to a very simple machine with S1 and S2, and they oscillate, and then in one case no B and then B. And the transition is always taken. So it's always true. It always happens that way. Okay, so this is a composite machine. So we had a finite state machine to begin with. We had the feedback loop, and we encapsulated that feedback loop and tried to find the machine that has the same behavior of the original machine plus the feedback. And this is it. And the way in which you compute is exactly the same as we did before. You assume something, you propagate, see what happens. You assume the opposite, and you see what happens. So that the method to compute what that finite state machine ought to be is always going through analysis of what happens to the various values of input. So this one is actually an ill-formed example, and in fact there doesn't exist any possible value. So in state S1, of course, there is Sn is absent. In state S2, there is no fixed point. You can't possibly work, right? Why? Because not A is not present, then you output B. But B is equal to A, and so how can it be B present and not present at the same time? Bad news, right? So this one is an inconsistent circuit. Finite state machine. Now, in this particular case, in S1, both Sn absent and Sn present are actually okay fixed points. So no matter what happens, you're always okay. Now, in state S2, we get the unique Sn equal to present because no matter what the value of A is, you always output B. So B is present there. So since state S1 is reachable through the transition mark with A, this composition is ill-formed again, right? Because we have a situation where we can have two solutions. So that is the other ill-formedness, that the solution is non-unique. Now, single signal, you start with Sn unknown, you propagate, and you see what happens to the composed finite state machine until you reach a consistent value. So it's still this idea of grinding the computation. So a finite state machine in which this iteration works is called a constructive machine because I have a way of building the solution. This one is a non-constructive, but is well-formed, meaning that if you try to apply the algorithm of grinding, you go nowhere. But yet, if we look at in its entirety, this machine is in fact giving nothing. So B is absent for all n, so nothing occurs. But I cannot use that idea of propagating because I don't know what to propagate. So for this situation where the constructive machine procedure doesn't work, then the only way to do is to look at all possible combination of inputs and see what happens. Right? So it's exhaustive search to build the composed machine. Now, sometimes you can get by using still the idea of a constructive, but with a minor variation. And this minor variation is about the main and must thing. So look at this machine and in state S1, and when we can immediately determine that this machine may not produce an output, right? Because if A is present, it doesn't do anything. The output is empty. Therefore, we can immediately conclude that the output is absent, even though the input is unknown. So no matter what the input is always absent. In state S2, we can immediately determine that the machine must produce an output, because no matter if A is present or absent, I always spit out B. So we can immediately conclude that the output is present. And so this one, with analysis may-must, I can then build the confidence that this machine is indeed, makes sense. Okay. Now, the constructive semantic for multiple signals is about the same. So now instead of propagating a single signal, I must propagate a bunch of them. And so what happens is that when I do the construction, I have to follow several signals. So I have to build all the, the valuation of all the signals. And so the constructive procedure is that you start with all unknown, and then you determine, you eliminate as many unknown you can, and then you iterate until eventually either you eliminate all unknown or not. If you eliminate all unknown, the machine is constructive, you found the fixed point. If not, it's not constructive, may or may not have a fixed point. Multiple actors, same thing. So if you have three FN, you combine them, and then you apply this very same procedure. And you can have an arbitrary structure, whatever you want, the machine is always the same. So now, a state machine language with constructive semantics will reject all the composition that in any iteration fail to eliminate all the unknowns. Okay? And in fact, the way in which you compute the fixed point, again, as I repeated before, is to do the propagation. And so if the propagation eliminates all the unknowns, happy. If not, not happy. And in fact, STRL will spit out, let's say, blah, right? So if the compiler will tell you, this feedback composition I cannot handle. It doesn't mean that it's not correct. I cannot handle it. Because STRL compiler is based on this construction. Some other programs, like, for example, Simulink, is preventing you from having a particular feedback that will cause these problems to occur. So you eliminate everything. So the compiler looks at it and says, no, I'm not going to do this. Right? So go away. Well, STRL will try to find the fixed point, and will come back to you and say, I found it or not. And if not, maybe it exists, but I don't know how to find it, so it rejects the thing. So in conclusion, so the emphasis of synchronous composition is always on determinate and analyzable. Now, we also found out that sometimes the analysis is very complicated. We have to resort to exhaustive analysis, but in principle it is possible. And so we have a unique answer to the question, is this well-formed or not? Now, the point is that automated tools like the compilers of the synchronous reactive languages will apply the techniques that we have seen before, because if you want to do it by hand, it's very tedious, of course. And if the circuit is large, you don't want to do that. It's out of the question. So, synchronous systems in general have fewer horrible behavior than asynchronous. The horrible behavior we've seen before are due always to a feedback composition, and the feedback in general, if it is with machines that the property of is always well-defined. So Moore machine is always well-defined, no matter what. But if you have Mealy machines in the structure, then you don't know, you have to do all the analysis that we said before. Okay? End of story. So thank you for the attention. To the next lecture.